Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to have you all in this particular space. And in this particular video here, we're going to be exploring some interesting concepts related to physical chemistry. Looking at physical chemistry, we're going to look specifically at the kinetic model of gases. This is actually important because you need to be able to predict various outcomes, like for example, looking at the collision frequency as expressed in this particular question, which says that how many collisions per second does a nitrogen molecule make at an altitude of around 15 kilometers, which is way above ground level. And here in that particular region, we need to take into conditions necessary like the temperature, which is actually measured in Kelvin, 217, and pressure to be around 12.1 kilopascals, and the area of that particular cross section of the tube, we'll call the tube, the collision tube, to be around 0.43 square nanometers, or we'll say nanometers squared. So looking at this, we need to go back into the specific idea of, hey, one, what is the nanotube? What is it conceived of? Two is, how are we going to be able to position these in terms of the right conditions necessary for this particular expression problem to be solved? And three, how is this applicable to nitrogen gas? So we need to go back to the basics, and the basics involves the following: looking at a specific tube which we're going to put in a particular condition, that in this case the condition is 15 kilometers in altitude. This collision tube, which I'm going to express as this particular term, collision tube, will have various properties that will be expressed. One is that this tube will have the radius, which is represented as d, to be equal to the specific diameter of our particle. And so our particle in this case is nitrogen gas, and nitrogen gas as a particle having the same diameter as the radius of the tube is going to move at a specific distance that is represented as the whole height of that particular cylindrical tube. And the height, or we'll say the specific length of the trip that the particle makes, is measured as the relative mean speed multiplied by the time. And so once we have this taken care of, another thing to consider is that while this particle is moving at a specific distance in this particular collision tube, there are a couple of things that are going to happen. It's going to collide with some particles, and it won't particularly collide with other type of particles. In this case here, if you consider this to be the heat region, which is when it comes in contact with a different gas particle or the same particle, we're going to consider this to be represented as B, and while this one here, which is where it doesn't actually collide with, is going to be miss, which is going to be represented as particle A. So where this particle E, because E is not taken here, E is going to collide with our specific molecules. And so once we have this expressed and determined, we need to now actually address the big elephant in the room. I'll put it that way. How are we going to express these particular conditions in terms of the collision per second? And the collision per second is actually represented as, going to represent here, collision per second, which is represented as time, is actually expressed as Z. And we're asking, what is Z? Z is known to be called the collision frequency. And so the collision frequency, we need to be able to derive this particular formula, and from there we're going to apply it to this particular question. Now in here, we need to notice that our specific relative mean speed is actually equal to our expression, which is the square root of 2 multiplied by the mean speed, where our mean speed is actually expressed as square root of 8 RT over pi M, where the big M is represented as the molecular weight of that particular gas molecule. So therefore, once we have this taken care of, we need to take the next step into consideration, which is to determine the volume of this particular tube right here. And to determine the volume, we need to determine what is the area, and we need to multiply it by the height. We know that the area is actually focusing on the space right here, and this space is represented as the symbol here, which is equal to pi d squared, where d is also the same as the diameter of that particular gas molecule. That is the assumption, and d is also represented as the radius of this particular tube. So therefore, our volume is going to be equal to this particular symbol multiplied by our height, where that symbol is actually expressed as pi d squared multiplied by our height, which is represented as the relative mean speed multiplied by the time. Therefore, once we have this taken care of, we're going to combine these two expressions here together in order for we to actually come up with some expression that is going to represent our volume. And so therefore, our volume is going to be equal to, in this case, pi d squared multiplied by our specific relative mean speed multiplied by our time. And so once we have this particular volume, our next thing is to be able to now focus on the number of particles right here. Now, to determine the number of particles here, we need to consider stationary particles in this particular space right here, are represented as A and B. Now, where we make that condition, taking that A and B are stationary, we need to then apply this into the moving particle specifically, which is in this case E, and E in this particular question is expressed as the nitrogen gas. So therefore, the total number of particles or stationary particles or molecules in this particular collision tube is actually equal to Na, and Na is equal to this particular interesting N symbol multiplied by the total volume. And in this particular part, we need to keep some terms actually, or define some terms. We're going to define the term of Na to be equal to the number of molecules, and we're going to define Vt to be equal to the total volume. And next is that we need to define what this particular symbol is, and this particular symbol actually represents the number density, and the number density as a result is equal to the division of our number of particles by the volume. So therefore, in this particular case, when we then express this in terms of the number of heat collisions at time interval by E on B. So on B, we're going to focus on B, which is here. We're going to see how E actually collides with B, therefore applying this in here, which actually tells us that, hey, we need to determine our now specific number of heat collisions. This is actually equal to our number density multiplied by our area multiplied by our specific relative mean speed multiplied by our time interval. So therefore, in this particular expression where we've determined the number of collisions at a time interval, we are going to take apart a specific segment of this particular expression, which actually will be an indication of a relationship with the number of collisions and then that particular per time. So therefore, if you divide both sides by our time, we'll be able to get this particular subject of the formula, which is here, to be in terms of Z, and Z, which is the number of collisions divided by our time interval, is actually equal to the number density multiplied by the area multiplied by the specific relative mean speed. So this is actually what we're going to be using in this particular question, and there are other deriving expressions that will be important in tackling this problem. Now take note here that our specific relative mean speed is equal to square root 2 multiplied by our mean speed, where our mean speed here is equal to square root of 8 multiplied by RT divided by pi multiplied by our molecular weight of the gas. Therefore, we actually have our relative mean speed to be equal to square root of 16 all multiplied by RT over pi molecular weight. So once you have this, we now have our new expression for our collision per time to be equal to the number density multiplied by the area multiply all square root of 16 RT over pi molecular weight. So once we have this taken care of, our next part here is how are we going to express this in terms of various gas laws? And various gas laws involves the following. We need to look at how we'll be able to change this expression of the number density, because we are not given the number density in this particular question. So to focus on that, we're going to look at how number density is actually related to various terms that we're going to express down the road. First is that we know that for our ideal gas law, P V is equal to nRT. Therefore, if you solve for n, we actually have this to be equal to PV over RT. And so take note that where our specific n is equal to the number density multiplied by the volume over our number of particles, take note that n is actually measured, the small n here is measured in moles. So therefore, this is going to be applied to this particular expression alongside K. K is represented as the Boltzmann constant, and the K is equal to R over the number of particles. And as a result of that, once we apply both to this particular expression, what we are going to have is, first we're going to have the number density over, we have the number of particles here to be equal to, next is P, which is the pressure, over R T, and we have our V. So take note here that the volume cancels out, and what we're left with is K is equal to R over NA. So therefore, if we remove our NA, our K is our gas constant, we're going to have our pressure to be equal to, in this case, the number density multiplied by our particular Boltzmann's constants multiplied by our temperature. So therefore, our expression now for N, which is the number density, is now in terms of the pressure over our particular K, which is the Boltzmann constant multiplied by temperature. Now, so once we're able to determine our expression now in terms of the number density, we're going to apply this now into our equation above, where we have our Z, which represents the collision frequency, now in terms of the Boltzmann constant and also the temperature and pressure. So therefore, putting this in here would then lead us to our new expression for Z, which is now equal to pressure over our Boltzmann's constant multiplied by the temperature, and all this is multiplied by the cross-section area, and this is all multiplied by the square root of 16 RT over pi molecular weight. So now we are able to determine this particular expression. Our next step is to then apply this to our specific problem, and so this is going to be where we're going to stop, and on our next video we're going to apply this to our problem, because this problem question here was kind of a long process for you to be able to feel comfortable deriving this formula and seeing various interest associations that you're going to have with respect to various of the collision frequencies related to not only the cross-section area, but also looking at how this is not really dependent on the pressure and temperature, because once you increase the pressure, that is actually an indication that temperature will increase. Therefore, when you have that ratio of the pressure in this particular case and temperature, that is actually cancelled out. So therefore, the collision frequency not really dependent on temperature, so that in this particular case, or I would say it's independent of temperature and pressure. So that's about it for this particular video. On our next video, watch out for the example here in detail and how to actually convert units and then arrive at your final answer. All the same, stay smart as always and believe in yourselves.